CBE 360. This is an excerpt from Marlin's textbook, Process Control and Dynamics. Chapter 4, Modeling and Analysis for Process Control. We'll learn about the introduction, the Laplace transform. Learn about the initial value theorem, the final value theorem, partial fractions. We'll learn about input models and transfer functions. This is the most important part of the chapter. We'll learn about the order. The order is the highest derivative of the output variable in the differential equation. We'll learn about the pole, the zero, the order of the numerator and the denominator, the causality, steady state gain. We'll learn about block diagrams, the frequency response, amplitude ratio. So these are the most important things in this textbook right now. For the time being, I will be reading parts of chapter 4. I'll be reading chronologically. So chapter 4. Section 6, the conclusion. The methods in chapter 3 and 4 can be combined in an approach shown in figure 4.11. Designed to provide models in the format most useful for the analysis of process control. The initial steps involve the modeling procedure based on fundamental principles summarized in table 3.1. Table 3.1 was the modeling procedure. And this procedure can be applied to each process in a complex plant. Then the transfer function of each system is determined by taking the Laplace transform of the linearized model. The block diagram can be constructed to present the interactions among the individual transfer functions, and the overall transfer function for the integrated system can be derived through block diagram manipulation. The overall transfer functions can be used to determine some important properties of the system without solving the defining differential equations. These properties include, I'll say this again, the overall transfer function can be used to determine some important properties of the system without solving the defining differential equations. The properties include the final value of the output variable, the stability of the response, and the response of the output to a sign input. This is important. I'm going to make an important differentiation. This is concerning transfer functions and not the Laplace transform. However, the transfer functions are frequently put into a Laplace transform. Also, determining this information without the entire dynamic response has two advantages. It reduces the effort to establish these system properties, and it assists in understanding the ways in which equipment design, operating conditions, and control systems affect these properties. And the properties were final value, stability, response of the output to a sign input. Naturally, information about the entire transient is not obtained by analyzing the poles of the transfer function or by the frequency response calculations. The complete transient response can be obtained if needed from analytical or numerical solution of the algebraic and differential equations. As noted in the previous chapter, many different processes, heat exchangers, reactors, and so forth, behave in a similar way. The transfer function method presented in this chapter gives us a useful way to compare models or processes and recognize similarities and differences. And that's the topic of the next chapter. Chapter 5 is titled Dynamic Behavior of Typical Process Systems. So I'm going to go ahead and go back into chapter 4, and I will read block diagram, and then I will read transfer functions. Block diagrams, section 4. The transfer function introduced in the previous section describes the behavior of the individual input-output system on which it is based. So the transfer function describes, maybe x over y, or maybe y over x, I forget which one it is, but x and y correlate to input and output. Reverse it. X and y correlate respectively to input and output. Often several different individual systems are combined, and the behavior of the combined system is to be determined. For example, a control system could involve individual systems for a reactor, a distillation tower, a sensor, a valve, and a control algorithm. So the overall model can be derived by writing all equations in a large set, taking the Laplace transform, and combining into one transfer function. Another approach retains the distinct transfer function of the individual systems and combines these transfer functions into an overall model. So instead of compiling the equations prior to taking the Laplace transform, you have the transfer functions distinctly labeled or identified, and then you combine the transfer functions into an overall model. And usually you just multiply them if they're in a series. So the second approach, which has individual transfer functions combined, and this is what we have been studying extensively. We have a process, and we have GS, GP, GC, GD. These are introduced in chapter 8 in the figure 8.1. So this approach, it retains individual systems, thereby simplifying model changes, different sensor model. It provides a helpful visualization of the cause-effect relationships in the overall system, and it gives insight into how different components of the system influence the overall behavior, aka the stability. The block diagram provides the method for combining individual functions into an overall transfer function. The block diagram provides a method for combining individual transfer functions into an overall transfer function. And this is the preferred approach. The three allowable manipulations in the block diagram are shown in figure 4.5, A through C. It seems as if we're not allowed to connect two inputs, aka x, into a process. Rather, we would have to connect the inputs into a pipe, a single stream pipe, write a schematic representation for the combining of the two streams, and then we have one single stream. Notice that I said previously that you would have to have a series to do multiplication, but if you have them in parallel, you would do addition. The first manipulation is the transform of an input variable to an output variable using the transfer function. This is just a schematic representation of the relationship introduced in equation 4.45. And I don't know what 4.45 is, so maybe we can go ahead and back up. So 4.45 is the baseline equation for the transfer function. The transfer function is the output over the input. The second manipulation is the sum or difference of two variables. The third manipulation is splitting a variable for use in more than one relationship. And these three manipulations can be used in any sequence for combining individual models. A more comprehensive set of rules based on these three can be developed, but these three are usually adequate. To clarify a few illegal manipulations, which are sometimes mistakenly used, that are shown in figure 4.5D through F, the first two are not allowed because the transfer function is defined for a single input and output. And the third is not allowed because the block diagram is limited to linear operations. The third is not allowed. Okay. So for this block diagram, this is a summary of the block diagram algebra. That's really useful to note. It's a very accurately descriptive title, block diagram algebra. If you have a summing point, it's a sum, not a multiplication of the two input. So the model reduction steps normally followed are 1 through 4. Define the input and output variable desired for the overall transfer function. Express the output variable as a function of all variables directly affecting it in the block diagram. And this amounts to working in direction opposite to the cause-effect relationship arrows in the diagram. So you start from the output to the input, so that's opposite of the arrows. So then next you eliminate intermediate variables by this procedure until only the output and one or more inputs appear in the equation. This is the input-output equation for the system. If a transfer function is desired, set all but one input to 0 in the equation from step 3 and solve for the output divided by the single remaining input. Again, if a transfer function is desired, set all but one input to 0 in the equation from step 3 and solve for the output divided by the single remaining input. This step may be repeated to form a transfer function for each input. The following examples demonstrate the principles of block diagrams, and many additional applications will be presented in later chapters. For the process in figure 6, we have a block diagram for example 12. We are given time constants and we're given k values as well, and we're given the transfer function for G1 and G2. Notice that the transfer function is not written explicitly in y and x. For the first transfer function, we have the output over the input, and this directly correlates with k over tau s plus 1. And I'm unsure how we end up getting to that conclusion of tau s plus 1. I've seen it pop up multiple times. I believe it's just a first order system. So I'm going to skip the example. I think it'd be more useful for me to study examples in the chapter 8. So examples that can be represented by the structures of example 13, along with the effects of the structures on dynamic behavior, will be presented in the next chapter. It is perhaps worth noting that the block diagram is entirely equivalent to and provides no fundamental advantage over algebraic solution of the system's linear algebraic equation in the S domain. So either algebraic or block diagram manipulation for eliminating intermediate variables to give the input-output relation will result in the same overall transfer function. However, as demonstrated by the examples, the block diagram manipulations are easily performed. Let's look at example 13. Provide the overall transfer function for the system in figure 7. The system in part A is a series of transfer functions for which the overall transfer function is the product of the overall individual transfer functions. We're saying that the overall transfer function is the product of the individual transfer functions. And this does not make any sense to me. Namely, it doesn't make any sense because we have no indication of y or x. We only have variables of x shown here. So the general formula that they're providing is the multiplication of I components of the transfer function is equal to the overall transfer function. And the overall transfer function is the output over the input. So when we're saying the overall transfer function is the product of the individual transfer functions, I guess that's correct. However, there's one instance in which we stated that we want to work backwards and we want to put the output as a function of all the external extremities. That's not the right word, but we want to put the output in a form that is a function of the transfer function as well as, the input. So if we have a series of transfer functions, we could just add them up. However, there's some better way to do this. Equation 4.62. So we have the output is equal to the transfer function times x. There's some more nomenclature that I didn't state. But however, we're supposed to derive the overall transfer function, so we will arrive at a transfer function. So for part B, we have a parallel structure of transfer functions, and the overall transfer function will not be multiplied, rather it will be added. And remember, when you write a transfer function, you have to follow block diagram nomenclature. So you have to have some point, and you have to remind yourself that a block diagram and you have to remind yourself that a transfer function is only used for a single input and single output. So we have 3 block diagrams considered in example 13. So for the third one, we have a recycle. The overall transfer function is not as simple as just multiplying or adding them together. Rather, you would have a denominator. So at this point, it's been 30 minutes. I'm going to take a 5-minute break. I'll come back. I'm not entirely sure if I'm going to continue this block diagram algebra. I think I've kind of figured out what's going on so far. I think it would be useful to go to the transfer function so I can learn about the poles. And then for the last hour, I'll read chapter 8 and chapter 9. So I'll pick up on section 3, input-output models and transfer functions.